That bathroom scale is lying to you. It's not measuring gravity, it's measuring the floor. And that single fact explains the strangest thing. You can be weightless while gravity is still almost as strong as it is here. So what are you actually feeling when you feel gravity? Put a bathroom scale on the floor, step on it. The number you see is what you call your weight. And already we've made a mistake, because the scale is not measuring how hard Earth pulls on you, it's measuring how hard the floor pushes back. That sounds like a word game. It isn't. It's the entire paradox. If weight is gravity, then why can you be weightless where gravity is still strong? Astronauts in the International Space Station are not out in some magical region where Earth stops pulling. The ISS is only a few hundred kilometers up. Gravity there is still most of what you feel on the ground, roughly 90%. If you could stand on an invisible platform at that altitude, you would still feel pulled downward almost as much as you do right now. So why are they floating? And here's the second confusion. People say there is no gravity in space. Then they show a satellite orbiting Earth, which is only possible because gravity is there. If gravity vanished, the moon would not politely keep going around us. It would leave, or fall, or do something else. It certainly wouldn't orbit. So we have two things that can't both be true. 1. Weight feels like gravity. 2. You can lose weight without losing gravity. That's the problem we're going to pin down. Now, when you stand on the floor, what are the forces? There's the gravitational pull downward, yes, and there's a push upward from the floor, what physicists call the normal force, meaning perpendicular, not ordinary. Your body is not in a calm diplomatic agreement with the universe. Your atoms are being squeezed. Your shoes compress. Your bones carry stress. The floor is pushing on you, and you are pushing on the floor. That push back is what your nerves interpret as heaviness. If the floor disappeared for a moment, gravity would still be there, but the pushback would be gone, and the feeling of weight would vanish instantly. That's already a clue. Weight is not the pull. Weight is the interruption of the fall. You can test this without rockets. You've felt it in an elevator. Imagine you're in an elevator, standing on a scale. The cable is fine, everything is normal. The scale reads your usual number. Now the elevator starts going up, accelerating upward. Not just moving upward, accelerating. You feel heavier. The scale number increases. Did gravity get stronger because the elevator decided to climb? Of course not. Gravity doesn't care about your building schedule. So why does the scale change? Because the floor has to push harder on you to make you accelerate upward, along with the elevator. Your inertia, your resistance to changes in motion, demands a bigger push. The scale is basically a little device that measures that push. Now reverse it. The elevator accelerates downward. You feel lighter. The scale number drops. Again, gravity didn't politely turn down. What changed is how hard the floor is pushing. And now take it to the extreme. What if the cable snaps? This is where people's intuition gets dramatic. They imagine maximum gravity and terror and falling. But the physics is strangely calm. The elevator, the scale, everything starts accelerating downward together at the same rate. So what does the scale read? 0. You are weightless in a falling elevator, even though gravity is doing exactly what it always does. In fact, gravity is the reason you're weightless in that situation. It accelerates everything together, so nothing needs to push on anything else to keep up. No floor pushing up on you, no squeezing, no stress in your bones, no scale reading. That is the basic observation. Weight is the force of the floor on you. When the floor stops having to hold you up because it's falling with you, you lose weight. Now, this immediately creates an uncomfortable question, because when you say I'm falling, you mean I'm being pulled by gravity. But in the snapped elevator case, gravity is pulling you, and yet you don't feel it. You feel nothing until you hit something. So what do you actually feel when you feel gravity? You don't feel the pull directly. You feel the push that prevents the pull from having its way. You can say it in one brutal sentence. Gravity is you not falling. Or if you want it more precise, weight is you not being allowed to follow the natural free-fall motion. That's why a scale is such an honest instrument. It doesn't care what story you tell about gravity. It only measures contact force, push, compression, stress, and this is why weightlessness is the wrong word. It makes you picture gravity being absent, but what's absent is support. The technical phrase is free fall. In free fall, you are moving the way gravity alone would make you move, with nothing else interfering. That's what orbit is. That's what falling is. That's what the ISS is doing around Earth. Now here comes the part that really bothers people. Orbit looks like you're not falling because you keep missing the ground. But orbit is falling. It's falling sideways fast enough that as you fall, the Earth curves away beneath you. You keep falling around the planet. The ground never catches up to you, so you never need a floor to hold you up, so you never feel weight. The astronauts are not floating because gravity is weak. They are floating because nothing is stopping their fall. And once you see that, the everyday experience flips inside out. Standing still on the ground is not the natural state. Standing still is the weird thing. Standing still requires a constant upward electromagnetic shove from the floor, atom against atom, preventing you from following your free fall path. That's why rest on the ground is actually a state of constant acceleration in a deeper sense. Not acceleration in the speeding up across the room sense, but acceleration away from the free fall motion your body would otherwise take. This is where the word force starts to get slippery. Because when you feel heavy, you say a force is acting on me, gravity. But what your body is feeling is not the gravitational pull, it's the support force. The force you feel is the interruption. You can even make it personal. Close your eyes and notice what weight feels like. It's pressure under your feet. It's the chair pressing on your legs. It's the bed pushing on your back. All contact, all pushing. Gravity itself is strangely silent. It moves you without squeezing you. If nothing resists, you don't feel it at all. So the real question becomes sharper. Why do we describe gravity as a force if the most pure gravitational motion, free fall, feels like no force? And the elevator trick is not just a cute story. It's the doorway into a much deeper idea. Maybe gravity isn't like the other forces. Maybe it doesn't push or pull in the same way electricity pushes and pulls. Maybe what we call gravitational force is actually about motion itself, about what path you take through the world when nothing is interfering. That's the paradox we're going to live inside for the rest of this. On the one hand, gravity makes apples fall and planets orbit. On the other hand, when gravity is the only thing acting, you feel nothing at all. So in the next part, we're going to slow the elevator down, frame by frame. We're going to separate three ideas people mash into one word: gravity, weight, and acceleration. And once those are separated, the ISS stops being mystical. It becomes almost inevitable. And then the final twist, this not a force but a path viewpoint, isn't poetry. It's a precise statement about how nature keeps time and space consistent for everyone. Whether you're standing on Earth, falling in an elevator, or circling the planet at 7.7 kilometers per second. So let's do the elevator again, but with a cold eye. No romance, just what moves how. You're standing on a scale. The scale reads some number. What is that number physically? It's the upward force the scale exerts on you. Call it N. The normal force, the push. If you are just standing there, not moving relative to the elevator, your acceleration is zero relative to the building. But you are not force-free. Two forces act. Minus gravity pulls you down. The scale pushes you up. N. The scale pushes you up. N. And since your acceleration is zero, those balance. N equals sine mg. That's the boring case. Now the elevator accelerates upward with acceleration a. You still stand on the scale, so you accelerate upward with it. Now forces are the same two forces, but they do not balance anymore. The net force upward must be die, so N equals sine mg equals sine ma, which means N equals sine m. The scale increases. You feel heavier. Not because gravity changed, because the required upward push changed. Because the required upward push changed. If the elevator accelerates downward with acceleration a, the equation becomes N equals sine ma, so N equals sine mg minus a, lighter. And if the elevator is in free fall, that means it accelerates downward at a equals sine g, then N equals sine mg equals sine 0. The scale reads 0. Weightless. That's not philosophy, that's just bookkeeping. Now here's the next step, the one that makes people uncomfortable. In the free fall case, gravity is still pulling with mg, so why isn't that a felt force? Because your body does not feel forces that act equally on every part of it. Your nerves feel squeezing, stretching, pressure differences. They feel your bottom being pushed more than your top. They feel stress. Gravity, to a very good approximation over the size of your body, pulls every atom of you downward with almost the same acceleration. It does not need to squeeze you to do it, so you don't feel it. But the floor is a bully. The floor pushes on the atoms in your feet, and those atoms push on the atoms above them, and so on. Your body is being compressed. It's like a stack of springs. That internal stress is what you interpret as weight. So the sensation of weight is not a gravitational sensation, it's a stress sensation. That's a huge reframe. You don't feel gravity, you feel support. Now take that and apply it to space. People imagine the ISS as being beyond gravity, but the ISS is basically a falling elevator that never hits the ground. Earth's gravity at that altitude is only a little smaller than at the surface. If you could freeze the station in place, hold it there with a magic rigid pole, you would feel almost normal weight. You'd need a floor pushing up on you. You'd have stress in your legs. Scales would work. But the station is not being held up. It is continuously falling. The astronauts are not floating because gravity is missing. They are floating because the normal force is missing. And you can make that concrete. In orbit, the station and the astronauts are both accelerating toward Earth. Same acceleration. So relative to each other, they're not dropping. They're just coasting together. They only bump into each other if somebody pushes off a wall. So far we've cleaned up one mess. Weight is not gravity. Weight is the support force. But we still have a second mess. We keep saying gravity makes you accelerate downward. That sounds like a force in the usual sense, like electricity, like a rope pulling. And yet in free fall you're as close to no forces acting as you can get. And still gravity is doing its job, bending your path toward Earth. So what is gravity then? If the most honest gravitational motion feels like no force.
Here's the way to think about it. There are two kinds of acceleration people confuse. One, coordinate acceleration. Acceleration relative to some chosen frame, like the ground, a map, a grid. Two, proper acceleration. The acceleration you actually feel, the one that shows up as stress in your body and a done-go reading on a scale. A scale measures proper acceleration because it measures contact force. If your proper acceleration is 0, the scale reads 0. In free fall, your coordinate acceleration relative to the ground is about g downward, but your proper acceleration is 0. On the ground, your coordinate acceleration is 0, but your proper acceleration is about g upward. Upward, because the ground is forcing you to deviate from the free fall path. That's the sentence that sounds insane until you chew it. Standing still on Earth means you are accelerating upward, away from free fall. Now, if that's true, then the phrase gravity is a force pulling you down starts to look like a choice of coordinates, a convenient story from the perspective of the ground, like saying the sun goes around the Earth. It's a description, not a deep mechanism. From the right viewpoint, the one that matches what you feel, free fall is the natural force-free motion, and being held up is the forced motion. So the paradox is not just why can you be weightless while gravity exists? The paradox becomes why do we call free fall falling at all, if it's the force-free motion? Because we are emotionally loyal to the ground. We take the surface of Earth as the default frame, and we judge everything by it, but the ground is not an inertial frame. It's being shoved upward by the electromagnetic forces in the material beneath you. The ground is resisting gravity, it's doing work, it's exerting force. So if you want the cleanest description of motion, no fake forces, no invented pushes, then you should attach your coordinates not to the ground but to a freely falling frame. Drop a little box with a camera in it. Inside that box, floating objects don't fall, they just hover. They drift. They obey the simplest version of Newton's first law. Things keep doing what they were doing unless something pushes them. In that falling box, gravity seems to disappear, not because it isn't there, but because you chose a frame that is moving the way gravity wants everything to move. This is the heart of Einstein's equivalence principle said without ceremony, locally, over a small region of space and time. Being in free fall in a gravitational field feels the same as being far away from gravity entirely. And the opposite is also true. Being held up in a gravitational field feels the same as being in a rocket accelerating upward in empty space. You can't tell the difference just by feeling. You'd need to look outside, do experiments with tides, compare signals, measure how the field changes over distance. But in your gut, in your scale, in your inner ear, support and acceleration are the same experience. Now that's a weird claim, so let's make it tangible. Imagine you're sealed in a windowless room with a scale, a ball, and a cup of coffee. Case A, you are on Earth, standing still. Scale reads. You drop the ball, it falls to the floor. Coffee sits in the cup. Case B, you are in deep space. Engines firing, accelerating upward at G. Scale reads. You drop the ball, it hits the floor exactly the same way. Coffee sits in the cup exactly the same way. From inside, it's the same physics, so what you call gravity could be reinterpreted as your frame accelerating, depending on how you set up the description. Now we're ready for the geometry idea, without jumping straight into curved spacetime like it's a magic trick. Start with a simpler geometry, a map. If you draw a grid on a piece of paper and you decide straight lines on this grid represent natural motion, then anything that deviates is accelerating. But you can play a trick. You can choose a different grid, a distorted grid, a grid that is stretched and curved on the page. Then some paths that looked curved before can look straight in the new coordinates. Same physical path, different description. That's what's happening with gravity. The force of gravity is what you have to invent if you insist on using the ground's coordinates as the default. From a freely falling viewpoint, the motion is straight as possible, and what looks like a force is really the geometry of the paths objects naturally follow. Physicists call those natural paths geodesics. But you don't need the word, you already know the idea, the motion an object takes when nothing is pushing on it. In ordinary space, that's a straight line at constant speed. In space-time near Earth, the straightest possible path is not what your intuition calls straight, because space and time themselves are arranged differently around mass. The free-fall path curves toward Earth, not because something is tugging on you like a rope, but because that's what straight means in the actual geometry you live in. And the ground is preventing you from taking that straightest path. So it must push, so you feel weight. That's the core swap. Minus free fall is straight motion in the real geometry. Weight is the sensation of being forced off that path. Now there is a catch, a very important catch. If gravity were perfectly uniform everywhere, you could transform it away completely by choosing a free-falling frame. It would vanish like a bad coordinate choice. But Earth's gravity is not uniform. It changes with distance. The bottom of you is slightly closer to Earth than the top of you, so the gravitational acceleration is slightly stronger at your feet than at your head. That difference is called a tidal effect. And tidal effects are the part of gravity you cannot transform away. They are the real fingerprint of curvature. They stretch and squeeze, even in free fall, if the region is large enough or the field is strong enough. That's why astronauts can still do gravity experiments in orbit. Tiny differences in acceleration still exist, and it's why near a black hole, free fall can become deadly, not because you feel gravity, but because different parts of you are pulled with noticeably different strength. So gravity has two faces. The part that looks like a uniform pull can be seen as geometry and coordinates. The part that shows up as tides is an actual variation in the geometry curvature you can't wish away. But for the everyday situations, elevators, ISS, jumping off a diving board, the uniform part dominates, and the weight story becomes clean. You are weightless whenever nothing is stopping your free-fall motion, and you are heavy whenever something is. In the next part, we're going to take this all the way to the existential punchline. The ground is not rest. The ground is a constant acceleration machine. And the universe is, in a sense, kinder than your intuition, because the motion you call falling is the closest thing there is to peace. Peace, that's a funny word to use for falling, but that's exactly the twist, because the thing you call gravity pressing on you is not gravity doing anything to you, it's the ground arguing with gravity, loudly, with electromagnetic force, atom against atom, like an invisible spring that never stops pushing. You can live your whole life thinking the ground is nothing, just a passive stage. It isn't passive. The ground is an engine, an accelerator, a device that continuously forces you off the free-fall path you would naturally take through space-time. It does that every second you stand, every second you sit, every second you sleep. So let's collect the story in one clean chain without hiding any steps. Gravity exists near Earth, in space, in orbit. It doesn't turn off. Weight, the thing you feel, is the normal force, the support force from whatever is stopping you from falling. A scale doesn't measure gravity, it measures that support force. That's why a scale goes crazy in an elevator. That's why it reads 0 in free fall. That's why astronauts float while gravity still pulls. So the paradox, how can you be weightless when gravity is still there, dissolves into a sharper statement. You can be weightless whenever you and your surroundings are falling together. The ISS is not the absence of gravity, it's a permanent fall. Now there's a deeper sting in this, because you were taught, maybe explicitly, maybe by the way people talk, that force causes acceleration. And we've just seen a situation where you accelerate a lot, and yet you feel no force. Free fall. And we've seen the opposite. You feel a force, your weight, while you aren't accelerating in the everyday sense. Standing still. So what you feel isn't acceleration relative to the ground. It's proper acceleration. It's being pushed off the natural path. In that sense, the strangest claim we've made is also the most accurate. You don't feel gravity. You feel the floor. That is why gravity is you not falling is not just a poetic line, it's a diagnostic tool. It tells you what your body is actually reporting.
Now take one more step, and it becomes almost existential. Think about what you call rest. A book on a table, a cup on the desk, you on a chair. We picture rest as the default. No forces, no drama, nothing happening. But if free fall is the force-free motion, then rest on a table is not rest. It is a constant deviation. The table is continuously pushing the book upward, preventing it from following its geodesic, its straightest path through space-time. So sitting still is in a certain sense a kind of constant acceleration, not across the room but through the geometry of motion. This is why the equivalence principle is so unsettling. It tells you that gravity and acceleration are not two separate categories. Locally, they are the same experience, and once you accept that, you start seeing the world differently. When you ride in a car and you feel pushed back into the seat, you say the car is accelerating. True, but what you're really feeling is the seat forcing you to deviate from the straight path you'd take if you were free. When you stand on Earth and you feel heavy, you say gravity is pulling me down. But what you're really feeling is Earth's surface forcing you to deviate from the straight path you'd take if you were free. It's the same sensation produced by different causes. In a rocket in deep space, the cause is engines. On Earth, the cause is the ground refusing to let you fall. That's why the elevator thought experiment is so powerful. It's not a trick, it's the cleanest place where your instincts admit defeat. You already know the feeling, heavier, lighter, floating. And those feelings track the support force, not the gravitational pull. Now, if you want to be very honest, there is one part of gravity you can't explain away as just coordinates. The tidal part. The part that changes from place to place. That's the part that stretches or squeezes. That's the part that makes the ocean have tides. That's the part that can pull a long object into a slightly different motion at one end than the other. That part is real in a way you cannot transform away. It's the fingerprint of curvature itself. But for the human scale story, the reason you feel heavy, the reason astronauts float, the reason the scale changes in an elevator, the tidal differences are tiny. What matters is whether anything is supporting you. So when someone says in space there's no gravity, you can answer without sounding mystical, no, there's gravity, but there's no floor. And when someone says I feel gravity, you can answer even more bluntly, no, you feel being prevented from falling.
Now here's the closing question. The one that makes all this more than a physics puzzle. Why does this matter to you? Because your everyday reality is built out of sensations. Up, down, heavy, light, standing still, falling. And physics is telling you, some of those sensations are not reporting what you think they're reporting. They're not direct perceptions of the external world. They're perceptions of contact forces of your body being constrained. Which means the universe is doing something slightly hilarious. The motion you're most afraid of, falling, is the motion that, in the language of physics, is the closest thing to no force acting. And the state you call safe, standing on solid ground, is the state where matter is pushing on matter as hard as it needs to stop you from taking that peaceful path. So the next time you step on a scale, notice what it's really saying. It's not telling you how much Earth loves you. It's telling you how much the ground is working to keep you from falling. And the next time you watch astronauts floating, don't imagine magic. Imagine an elevator cable that never snaps because there is no building, just motion, just geometry, just a continuous fall that never ends in a crash because the planet curves away. Gravity isn't a hand grabbing you. It's the shape of the possible paths you can take. Weight is what you get when something says no. Not that path, stay here. If you want to keep going, if you want to understand why straight lines can curve, how clocks and gravity are tangled, and why space-time geometry isn't an analogy but a measurable thing, then stay with this way of thinking. Don't memorize definitions. Keep asking, what would a scale read? What would you feel? What is actually pushing? Because the fastest way to get lost in physics is to trust words, and the fastest way to find your way back is to trust experiments. Even the tiny experiment of standing on the floor and realizing that feeling in your legs isn't gravity, it's you not falling.